welcome to a new final project presentation ceremony. Today we have one presentation prepared for today's ceremony. It's going to be by Ahmad, one of our students that is ready to go on and show us what he did for his final project. It's going to be based on perception, on doing visual camera calibration, but I don't want to explain anything. It's better if he can directly introduce his project to all of you. So let's say hello to Ahmad. Hello, Ahmad.
Hi, thank you very much, Alberto.
So it's all yours. You can introduce your project and start with the presentation.
Okay. So let me share the screen. Okay, can everyone see?
Yes, we can see it. Visual calibration.
Excellent. Thank you very much, Alberto. Hi, I'm Ahmed, and today I'll be taking you through my final project, which is visual calibration. So what is it about? So imagine a Starbucks cafe, which is a robotic barista platform that will prepare coffee autonomously. There is a camera on the sidewall that will aid it in its tasks. And we want to have it calibrated so that we know where the objects visible to the camera are located relative to the arm. So the goal of the project is to develop a calibration system that estimates the pose of the camera relative to the arm. We're going to use the camera itself to do that. And to aid it, we have an Aruco marker that will help us identify where the arm is, and we could perform the calibration that way. And we will use a web interface to perform this calibration on demand. The question is, though, why do you want to do it visually? If both the manipulator arm and the camera are fixed, wouldn't it be just better to take empirical measurements at the point of installation, measure it out? In an ideal world, that would be the case, but in reality, the location of the camera can drift over time due to slippage, vibrations, or other environmental factors. So periodic recalibration is necessary, particularly since the robotics barista's tasks are sensitive to, to accuracy in the camera pose. So let's specify it concretely. What are the components and deliverables? So it's going to be hosted on a ROSJack cloud instance provided by the construct and deployed for the Starbucks cafe lab they have there. The hardware is a Universal Robots UR3 manipulator arm with the marker placed, and there's a depth camera. And for software, we have ROS2 Humble with Move It 2, and I was given a gazebo simulation of the hardware environment. Those asterisks tell you that there's some nuances on the matter, which we'll get to later. And for deliverables, as mentioned earlier, we need ROS2 packages to implement the visual calibration and a web app front end to operate it. And specified in the sheet, but not possible, is for it to be containerized in Docker images. So I've kind of explained it, but probably it would be nice to see what it would look like. We're going to do a demonstration later on, but I'll just briefly show you a video just to kind of give you a taste, on a simulated environment, how it would work. So you'd have, an interface with a web that shows you where the arm is. You specify where you want it to perform, the calibration settings. And then, after you've kind of set it up, it would start to move into the area and perform the calibration. And if you're happy with it, by the end of the calibration, you can click publish, and you have yourself a calibrated camera. So then you could do all the perception tasks that you'd like to do for the robot. So, come on. Excuse me, sorry. Okay, there we go. Sorry, there was a slight error there with my my presentation. Here we go. So coming back, how do you go about designing it? The first thing we want to ask is, how do we approach finding the camera pose? So I'm proposing a numerical approach where I take sample pose estimates at various positions within the camera for view of the camera, and then we can take a best fit estimate based on those samples. For simplicity, we're going to be fairly naive and just treat all of them equally, because we don't know how the error is compounded depending on where the arm is relative to the view of the camera. So we're going to break this down into three. We have pose estimation, sample collection, and pose averaging. Those are the main tasks. So for pose estimation, you got to find where the marker is, and for that you have a package on OpenCV to detect the markers. That's basically the corner points of the marker on the image plane. So that's two-dimensional. So then you have to also turn it into 3D pose estimation. Since the setup has a depth camera, you can ideally directly get the 3D pose of the centroid of the marker. But unfortunately, the camera in the simulation and the camera in the real environment are different. So I had to abandon that, and I've gone instead to the 2D to 3D pose estimation method using the PNP solver that OpenCV recommends, which basically takes the camera intrinsics and the dimensions of the marker, and then it can interpolate where the marker is relative to the camera. And then what we do is then we chain that with the TF transform from the base to the marker. And then what we have is the full transformation from base to camera. Okay. So second question now is sample collection.
Can you hear me?
Sorry? Yes.
Okay, just one second, because I know that you have your project set up and everything, and I don't want the inactivity system to trigger. So just a reminder to go there and do a couple clicks so that you don't have to open everything again. Okay.
Yeah. Okay.
All good.
Right. Okay.
Yeah. Sorry for the interruption.
Not at all. Thank you very much, Alberto. So going back to the sample collection part of our of the calibration system. So so we said we wanted to move the arm around within the view of the camera to collect the samples of the position of the marker, and then we could get the best fit. What kind of path should we make? So I'm basically proposing that we do a path that's along the image plane. And basically it can be either circular or spiral, which will allow you to kind of perturbate the pose, both in translation and orientation relative to the camera. And it's gentle, so it's not huge differences. So you'd think that it'll take, it's not going to knock it off too much to take the average. Spiral will be more concentrated in the middle, but slightly askew to the side, whilst the circle is more uniform. There's also the ability to deflect on the z-axis if you want to have extra depth going downwards as well. Sampling is continuous, so basically, going to have it buffered and then done in batches. We'll talk about the batching in a minute. Okay. And last but not least, the averaging. So we have all of these raw pose estimates that we've generated through our sample collection, and we want to average them out. So at each batch, you'll take an average where the position is just the Euclidean norm, which is fairly trivial. But for orientation, that required a little bit of research, because with quaternions, unlike when we're talking about position where X, Y, and Z are all orthogonal, you could just take the average of each separately. The components of a quaternion are all dependent. So I had to look up how you'd take an average of them. That's the method I found from this paper by Mark Lee et al. And then after each batch, you want to basically accumulate what your average is. And so I'm just taking a cumulative average. For position, that's again simple. You're just adding the weighted sum. Whilst for orientation, I went by using spherical linear interpolation. Is that how it's pronounced? SLURP method to do that same task. So that's the process for averaging. And so now we have all the pieces together. Let's get it all integrated into one. So we have a calibration action server, which moves the arm to an initial pose and then performs the sequence. It'll be using MoveIt to control the robot. So you need to do a MoveIt configuration, load up scene collisions. And the other piece is a TF broadcast service, which allows us to programmatically publish a static transform. So when we are happy with the camera pose that we've estimated. And we also have a web app interface to operate the system. So that uses the Rosbridge WebSocket at the back end with a web video server and TF2 republisher and all of that to get it going. And at the front, you'd have roslib.js and rust3d.js. So as you saw in our little preview, that you get a 3D visualization pane that shows you the arm and the settings that you set for the manipulation, and you have a preview window showing you the live view of the camera, which is annotated with the marker, as it's performing the. So as it looks in terms of an architecture, you can see here the user-facing topics on the right. The action interfaces, the service interfaces, the image topic, and then on the left are how it interacts with the backend system. So that's the basics, and now we're ready to do an interactive demonstration. So we're going to switch over. So as you can see, we have it's all loaded here. So we're going to get the Rosbridge address so that we can log in, and we will connect. There we go. So you can see the robot. And this is the initial pose that we've set it and the path settings. So let me just do make it just a flat. So that's just a flat spiral, as you can see. Or we could just do a helix, or circle in the case, since we're not actually deflecting on the Z. And we have the ability to both to reset the average between runs, or we can accumulate them over different runs so that we can actually refine the process. So let's just turn that on. I know that it's kind of further away to get a good reading with the marker. That's 39. I think that should be a good one. So let's start it up. And it started moving. Unfortunately, with the real robots, the update rate for the backend topics with ROS are very slow. As you can see, it takes a very long time to update and see what's going on. But hopefully, despite that, we'll still get there. So it did find an average pose. You can see here, that's what it returned. And if I'm happy with that, does that look right? I guess so. I can just go play publish. It only actually managed to get one sample in, which is really pathetic. But unfortunately, there are transport issues. But so that's one of the kind of challenges with the live robot, and something that we could try to optimize. But maybe that would require a complete rework of the approach. But like I said, there is the option of just going again, or with a slight change, if you like, or even just the same settings, and have it. Let's maybe get it further away, and then it will have more samples to play with that way. So moving it now. So here we go. The update rate is very slow. I apologize. So, again, it's only managed one. So, we'll be happy with it, and we're just going to go publish. And there we go. That's that. Okay, let's come back to the presentation and talk about the journey. So, as you can tell, there are some challenges. In getting there. And so there are very real issues that hinder development. So first of all is the inconsistency between the real and the sim environments. So as I mentioned earlier, the cameras are not the same. They're different models with different field of view, different topic names. They publish depth a different way. One does a depth cloud, the other one does a depth image as a separate camera topic. So you can see here the different field of view ones wider. The robot had also, in terms of the robot description, it is different. The controller names are different. The name of the Aruco link, marker link is different. And it's also upside down, as you can see. Here it's facing this way, and here it's facing the other way. And the last but not least, the biggest problem, for me at least, that slowed me down, are the material differences in the scene. So the wall in the real lab is actually a lot closer than in the simulation. There are extra furniture like a cup holder, clamps, stuff like that. And it's also a bit more inset away from the lip of the counter. So the collisions that you kind of generated from the simulated environment that you kind of curated from that don't actually fit the real environment and required modification for you not to kind of hit things, which is a bit difficult because you have to eyeball it because you're not there at the physical lab. And I've had a few run-ins with that cup holder, as people will attest. Other issue are compatibility issues. So one is the lack of Docker support on the ROSjet, so precluded the Docker part of the requirements. And there was for the web interface, there were also big issues with support for ROS2 with the robot web tools efforts packages. So for the ROSBridge backend, you need to use a forked TF2 web republisher because the standard one was not updated for ROS2. And at the front end were bigger problems. So roslib.js was updated for ROS2, but it's kind of patchy. And ROS3D.js, which is the one for visualization, had real problems. I mean, it took a lot of finessing to actually force it to load up the robot description, pass the URDF correctly, and also update with the TF client. So, needed regular expressions to strip the leading backslash that it adds to the frame IDs. It had to manually pass the URDF. It was a nightmare, but we got there in the end, and that's the important thing. So we've seen it working, but we want to find out how well did it do. So for that, we need to do some testing. And for that, I For the components, that's you can do some basic G tests, which is what I did, where you can validate that the expected behavior happens. Although I will stress that they weren't stress tested in the sense that kind of looking for outlier kind of behavior type of thing. It was just that in an average case, it will work. It will work. So for integration and also for performance testing, you need a bit more to do that. So one thing that I did was to create a minimal SEM environment to simplify the process. So it's just the simulation, as you saw, I think a preview 2 slides down, is very basic. It's just the arm and the camera, and nothing in the way in terms of furniture and anything to kind of get in the way. So we've got this simplified test environment. We also need the ground truth to test against. So I also looked up at the files that were given, had to kind of read through where the camera was in the simulation and use that as a reference. So in terms of integration testing, that was done kind of ad hoc. That you just get it running, see it works. But for the performance testing, where we want to get some quantitative data for how well the calibration system run, I had an automated script that basically does a grid search with 3 different distances from the camera and various offsets in terms of translation and in terms of rotation. So basically, we're seeing in terms of how well it performs in terms of how well you kind of initially place it. And for that, I just used for simplicity the same path settings, which was just a circle of 2.5 centimeter radius and no Z deflection, and generated from that 242 simulations. So now that we've done that, how did it perform? Well, not too bad. So first of all, the good news is that it's not very sensitive to the positioning of the arm. So where you set it as an initial pose doesn't affect its performance that much. So there's no large correlation between the translation offset, angular offset, or distance from the camera. In terms of how well it performs, again, it was fairly accurate and resilient. There's a centimeter mean translation error and 2.4 degrees orientation error. And it's well packed, near the, so sorry. Yeah, it's tightly packed. So it means that, the standard deviation is very small. So you can expect with a high level of confidence that it shouldn't be more than, a centimeter or 2 away from the. As for the real environment, obviously we can't do quantitative tests because we don't have a reference in terms of where the robot is and where the camera is in the lab. But from ad hoc testings like we've just done right now, we could see that the behavior is generally correct. But there are also some takeaways in terms of some shortcomings when using it in the real lab. First and foremost is the sampling performance is highly degraded due to message transport delays. So when you saw how sluggish it looked, it's not because the package is caning the system in terms of computation. I had run it in previous times with HTOP, and neither in terms of memory or in terms of CPU was it really kind of pushing the system. It's very much in terms of the underlying message transport system that ROS2 is using, the middleware suffering in the real lab environment. So the upshot of that is that you're averaging over a small number of samples, which if the kind of thing that we're doing is that we're sampling multiple times to get a refined pose, then you're degrading its performance that way. But the fact that we can do repeat sampling means that we can get there eventually, even if it means that we have to run it a few times. So I think that's a silver lining. So that's about it in terms of my presentation. I now would like to say thank you for listening and open the floor for question and answers.
Okay, thanks a lot, Ahmad. Let's give you applause. Okay. All right, so very interesting presentation, as Ahmad himself said. So now it's time for questions. So please, the ones that are here in the YouTube live, you can write down any questions that you have for Ahmad related to his project, and I will be reading here the chat and translating the questions for him, for Ahmad. All right, so let me start myself. So I found very interesting that feature that you had in your website, that you can change like the trajectory of the arm, right, from a spiral to circumference.
Yeah.
So could you show us? So basically, changing the trajectory of the end effector, let's say changes, right, and then you have different type of samples, or.
Yeah, so let me share again to show you.
Maybe what I was going to suggest to see it better is because of because as you said already, the image topic is laggy, so we cannot see that very well. Maybe you can show us that from the lab camera. That might be probably we can see better that behavior.
Okay. So let me start sharing again. Okay. So okay. So at the moment we have it set up like this. So what shall we do? Shall we add a bit of roll maybe, just to?
Yeah, for example.
Okay. So now when it performs it, the arm is going to be tilted slightly. I think that should be fairly safe like this. Okay. So as a reference, you can see the orientation of the robot is fairly perpendicular there. But if we do a new run now like this, you can see now it's more tilted as it performs it.
Yeah. And now it's following like this. It's a circumference, right? Now, right?
Yeah. So and it's completed it now. So as you see, when I was kind of setting it up, you can see the path that it follows. So it's those green waypoints there. So, you can change the radius. You can add deflection so that, it spirals downwards. And like I said, you can change the,
changing the shape, for example, to helix. Do you notice any difference in performance? Is it better? It doesn't really matter that much.
So like I said in the presentation, for small changes, it doesn't seem to make a huge difference in terms of where the marker is concentrated within the image plane. But I do think that there is like a sweet spot in terms of distance away from the camera, where as long as you're not too far to the edge of the image plane, you're okay, and you're not too far away from the camera in terms of distance, because obviously the further away, the more the detection errors for the original mark estimation, because you think it'll only be as accurate to the resolution of the image that it's based on. So other than that, I don't think it makes a huge difference. But we can do a little try now and see, you know, oh, it's going to do a full loop around to get there. So I guess there's two questions for the real robot. Where because there's an issue of it getting readings at all, if it's doing small movements around one area and it's not keeping up, would it be more beneficial for it to move more or for it to move less? And I don't think there's going to be much difference with the image transport. This is entirely an issue of the estimation. You see here, it didn't manage to get a single one. So I do think for the real robot, getting it to move more seems to help a little bit. But I don't understand why. In the simulation, it doesn't make a difference. So yeah, but that's the current situation I have with it. Like I said, that there are kind of there is scope for improving this because, like I said, its performance is not that robust in the real robots. Not because of how the underlying calibration system works, which I think works fine, but it seems to be just in terms of integrating it with the real robot. You have all of these introduced problems in terms of, if you're not getting any samples, then there's nothing to average over. So that's the big issue. But if you have a reasonable number of samples, so when you run the task in the simulation, it's able to grab like 40 samples when it does a path round. So that's more than enough for it to get a good average. But when the number of samples it gets during the whole maneuver is like one or two, that all becomes moot in terms of which shape did you pick, how big the radius, where did you position the arm to begin with. So that's the kind of situation this system is in at the moment. I hope I answered your question.
Yeah. Really, interesting. So, in the real environment, as you were saying, there's a much lower rate of publication of the images. So, I assume that is affecting the samples you are able to get, right?
Yeah. So I have actually set up within the system that the action interface, you're able to set the sampling rate and things like that. So it is something that could be finessed if maybe you ask it to sample at a slower rate to begin with, that it might improve. But these are the kind of parameter tuning that it's something that you do with extensive testing on the real robot.
Okay. Yeah. That I see is one of the questions that I have here in the chat from Girish. Then also another question from Girish, for example, is how were you able to verify that the calibration is correct?
For the simulations, like I said, I took the ground truth, which is by looking up the robot description, Ezquerro, and looking up where the camera is spawned, I know where it really is. So when I run the automated testing script, whenever it comes back with the estimate that it has, I have a reference to benchmark it against. So when it was doing those 242 simulations, when it finishes the sampling, it returns with the pose that it thinks it's in, which we saw earlier. And what I did was then I compare that and add that into my table that I then performed the analysis later on.
Okay, but were you doing all that process? I'm curious. In this case, so were you doing all that process manually of launching the simulation, or did you automate it
No, no,
somehow?
it was an automated script. So
Okay,
I
okay,
had a
okay,
Python script which did a grid search.
okay, 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 okay.
Yeah.
Yeah, that's actually pretty interesting. Um, all right, Ahmad. So I think we can already leave it here. So yeah, thanks a lot for your presentation. I see, and I know also that you have worked a lot on it and dedicated a lot of effort to it. So having finally completed it and with a good result. So congratulations from my side. And yeah, if you want to say
Thank you very much.
some last words.
I'd just like to thank everybody at the Construct, you, Ricardo, and Girish, and everyone at the team for their support. And I hope for whoever watched the presentation that they found it useful. And thank you very much for having me.
All right. So yeah, if can you for one moment stop sharing the screen, Ahmad, so that we can all say hello, goodbye to you. Okay, and there you are. All right. So yeah, thanks again, Ahmad, and we'll be talking soon for the internship and for the next steps. So yeah.
Fantastic. Thank you very much, Alberto.
All right. All right, so for the rest, I hope that you enjoyed the presentation. I hope that you have been able to get some insights and you have been able to learn some things from the very interesting presentation by Ahmad. So yeah, hope to see you all in the next ones. We are going to be having more presentations by the end of this month and very likely many more in the months to come. So hope to see you all there. And yeah, so see you, and as always, keep pushing your robotics learning. Bye-bye.